Mechanics is a branch of physics that deals with the behavior of very small particles like atoms, electrons, and photons. Unlike classical physics, which describes the macroscopic world, quantum mechanics explains the microscopic world with different rules. At its core, quantum mechanics reveals that particles can exist in multiple states at once, known as superposition. Furthermore, particles can be interconnected in ways that defy classical logic called entanglement. These concepts challenge our traditional understanding of the universe. The inception of quantum mechanics marked a significant shift in our understanding of the physical world. It has paved the way for many modern technologies, such as semiconductors, lasers, and MRI. Understanding quantum mechanics holds the potential to revolutionize technology, medicine, and our understanding of the universe. Quantum computing, for example, promises to solve complex problems beyond the reach of classical computers. Let's dive deeper into the fascinating world of quantum mechanics. The birth of quantum mechanics dates back to the early 20th century, with contributions from Max Planck, Albert Einstein, and Niels Bohr. Planck introduced the idea that energy is quantized. Einstein explained the photoelectric effect, showing light as particles or photons. Bohr applied these ideas to the atom, leading to the Bohr model. Electrons orbit the nucleus in specific quantized orbits. Heisenberg, Schrödinger, and Dirac made further contributions. These advancements laid the foundation for modern quantum theory. Classical physics, also known as Newtonian physics, describes the macroscopic world, dealing with objects we can see and touch. The laws of classical physics are deterministic, predicting the future behavior of objects with great accuracy. Quantum physics, on the other hand, describes the microscopic world, dealing with particles like electrons and photons. The laws of quantum physics are probabilistic, predicting the likelihood of an event occurring. One key difference is wave-particle duality. In classical physics, objects are either particles or waves, but not both. In quantum physics, particles can exhibit both wave-like and particle-like properties. This duality is a fundamental aspect of quantum mechanics. Another difference is the principle of superposition. In classical physics, an object can only be in one state at a time. In quantum physics, a particle can exist in multiple states simultaneously. This principle is famously illustrated by Schrödinger's cat thought experiment. These differences highlight the unique and counterintuitive nature of quantum mechanics. Next, we'll delve into the dual nature of matter. Wave-particle duality is one of the most intriguing concepts in quantum mechanics. It suggests that particles, such as electrons and photons, can exhibit both wave-like and particle-like properties. This dual nature challenges our classical understanding of matter and energy. The concept was first introduced by Louis de Broglie in 1924, and confirmed by experiments like the double-slit experiment. In this experiment, electrons fired at a screen with two slits produced an interference pattern characteristic of waves. However, when observed, the electrons behaved like particles, creating two distinct impact points. This switch between wave-like and particle-like behavior depending on observation is a hallmark of quantum mechanics. Wave-particle duality has profound implications for our understanding of the universe. It suggests that the nature of reality depends on how we observe it. This idea is at the heart of many quantum phenomena and challenges our classical intuition. It also raises fundamental questions about the nature of measurement and observation in quantum mechanics. Let's explore Schrödinger's cat and the principle of superposition. Schrödinger's cat is a famous thought experiment illustrating superposition. Proposed by Erwin Schrödinger in 1935, it involves a cat, a radioactive atom, a Geiger counter, poison, and a hammer. If radiation is detected, the hammer breaks the vial, releasing poison. Until the box is opened, the cat is in a superposition of alive and dead states. The radioactive atom is also in a superposition of decayed and undecayed states. Observing the cat collapses the superposition into either alive or dead. Schrödinger's cat highlights the bizarre nature of superposition. It challenges our classical understanding of reality. Superposition has practical implications in quantum computing. This property gives quantum computers immense processing power. Next, we'll discuss Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics. Proposed by Werner Heisenberg in 1927, it states that we cannot know both the exact position and momentum of a particle. The more precisely one is measured, the less precise the other becomes. This arises from the wave-like nature of particles. A particle's position is linked to a wave packet with a certain spread. Narrower wave packets mean precise position but less precise momentum. This principle has profound implications for our understanding of the microscopic world. Quantum entanglement, spooky action at a distance. Quantum entanglement is a phenomenon where two particles become interconnected, so the state of one instantly influences the state of the other, regardless of distance. This phenomenon was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in a 1935 paper, often referred to as the EPR paradox. Einstein called entanglement spooky action at a distance because it seemed to violate the principle of locality. In an entangled system, measuring the state of one particle instantly determines the state of the other, even if they are light years apart. Entanglement has been experimentally verified numerous times with particles such as photons, electrons, and even larger molecules. These experiments show that entangled particles exhibit correlations that cannot be explained by classical physics. Quantum entanglement has practical applications in emerging technologies like quantum computing and quantum cryptography. In quantum computing, entangled qubits can perform complex calculations more efficiently than classical bits. Quantum mechanics is notoriously difficult to understand because it defies our everyday experiences and intuitions. In the macroscopic world, objects follow predictable paths, and their properties can be measured with great precision. However, in the quantum world, particles behave in ways that seem bizarre and contradictory. One reason quantum mechanics is counterintuitive is the concept of superposition. The idea that a particle can exist in multiple states simultaneously is foreign to our everyday experience. In the macroscopic world, an object is either in one state or another, but not both. Another counterintuitive aspect is wave-particle duality. In classical physics, objects are either particles or waves, but not both. The idea that particles can exhibit wave-like behavior and vice versa challenges our conventional understanding of matter and energy. The probabilistic nature of quantum mechanics also contributes to its counterintuitive nature. In classical physics, the future behavior of objects can be predicted with great accuracy. In quantum mechanics, we can only predict the probabilities of different outcomes. Understanding quantum mechanics poses significant challenges due to its abstract and non-intuitive concepts. One major challenge is the mathematical complexity involved. Quantum mechanics relies heavily on advanced mathematics, such as linear algebra and complex numbers. These mathematical tools are essential for describing quantum systems but can be daunting for those without a strong mathematical background. Another challenge is the abstract nature of quantum concepts. Ideas like superposition, entanglement, and wave-particle duality do not have direct analogs in the macroscopic world. This makes it difficult to form mental models and intuitively grasp these concepts. The inability to visualize quantum phenomena adds to the difficulty of understanding them. Quantum mechanics also challenges our classical notions of reality and measurement. In classical physics, objects have well-defined properties that can be measured without altering them. In quantum mechanics, the act of measurement itself affects the system being measured. Despite these challenges, significant progress has been made in understanding and applying quantum mechanics. Quantum mechanics may seem abstract, but it has practical applications that impact our daily lives. One well-known application is in electronics. Semiconductors, the building blocks of modern devices, rely on quantum mechanics. Another significant application is in medical imaging like MRI. MRI uses quantum properties to create detailed body images. Quantum mechanics is crucial in developing lasers. Lasers are used in telecommunications, medicine, and manufacturing. The future of quantum mechanics holds immense potential for advancing technology and expanding our understanding of the universe. One of the most exciting prospects is the development of quantum computing. Quantum computers use qubits, which can exist in multiple states simultaneously, to perform calculations at speeds far beyond the capabilities of classical computers. Quantum computing could revolutionize many fields by solving problems that are currently unsolvable. For example, it could lead to breakthroughs in cryptography by cracking complex encryption codes. It could also accelerate drug discovery by simulating molecular interactions with unprecedented accuracy. Another promising area is quantum communication. Quantum communication uses the principles of quantum mechanics to create secure communication channels. Quantum key distribution, or QKD, allows for the secure exchange of encryption keys, making it theoretically immune to eavesdropping. This technology could transform cybersecurity by providing unbreakable encryption. Advances in quantum mechanics could pave the way for new theories and discoveries that challenge our current understanding of physics.